I'll be sharing this next session. Thank you very much. A well-known session in the Open Foam workshop since Exeter is the Splash Talks. Unfortunately, we don't have Bernard with us today live. Hopefully, is attending and supporting the Splash Talkers. So I invite all the Splash Talkers to come to the stage, please. All the persons that submitted. And you know the rules. 3 minutes for all the presentations. You have 3 minutes to present your work, to share the work with the community, and that's it. After 3 minutes, we move to the next speaker. So let's check the order of the presentations. So, oh, yeah, you already, you are already, okay. So you are already aligned with the, so please, can we have the slides in the, so, first speaker is Teng Jian from the College Energy of Power Engineering from the University of Aeronautics and Astronautics, Nanjing. Please.
Thank you very much, Professor. Good morning. Today I want to share how to generate the RES turbulent inflow libraries using the precursor simulation method. As we know, the RES and DNIs are very sensitive to the turbulent inlet. So here we present the library-based precursor simulation method to generate the turbulent inflow for RES or DNIs. For example, we are simulating a turbulent jet flow, and the jet inlet needs very accurate velocity fields with the spatial and temporal correlations. So here you only need 3 steps to do the job. First, do a precursor simulation like a periodic pipe flow, and then sampling the data from a slice and through the surface sampling function in OpenFOAM, and then gather the sampling data and store them in a database in HDF5 format. And this is the turbulent inflow library. And finally, use this boundary condition to map the velocity data in the library to the inlet patch of the main simulation. So based on the work of Mukha, we developed a new OpenFOAM boundary condition, precursor HDF5, comparing to the original time-varying mapped fixed value method. It has the following features. First, the HDF5 library file provides faster I/O speed, and so there is no need to deal with tons of time folders or velocity folders. And you can rescale the turbulent inlet velocity based on experimental data or your user-defined profiles. And most importantly, it supports the reuse of the precursor library during the main simulation. For the data rescaling, we use the method proposed by Schluter at 2005. So as you can see, unlike the synthetic turbulence method, in this method there is almost no mathematics in this method. We have validated the boundary condition in turbulent jet flames. Here are the results of Sandia D flame, and we compared the library method and library rescaling method with other synthetic turbulence methods, and this boundary condition provides good performance. We have made the code public on GitHub, and this is the link to the repository, and you can find more details in here. And special thanks to Dr. Mukha's wonderful work. We cannot finish this without them. Thank you very much.
Thank you. Perfect timing. So, next speaker is Soei Arisaka. Please go ahead.
Good morning, everyone. I'm Sohei Arisaka, a researcher at Kajima Corporation. I'd like to talk about our recent work accelerating legacy numerical solvers by non-intrusive gradient-based meta-solving. In this work, we want to accelerate numerical simulations by machine learning, but not to replace with machine learning. In short, we learn how to solve the problem rather than predicting solutions. More specifically, the machine learning model learns how to choose a good hyperparameters of existing methods. By this approach, we can utilize well-established legacy codes like OpenFOAM without modification and minimize black box path. If we can choose good hyperparameters, the simulation gets faster, but keeps same accuracy and reliability because the solution is computed by legacy codes, not by machine learning. Let's think about a typical example, learning how to solve linear systems by iterative methods. Here is a high-level architecture. The task information, in this example A and B, is fed into the neural network called meta-solver, and the meta-solver generates a solver parameter. For example, it can be initial guess of the iterative method or preconditional or some other parameters. And then the solver using the generated parameter, solver solves the task. After getting the solution, we can compute loss such as error of the solution or computation time to get the solution. Then to update the meta solver, we backpropagate the loss and compute the gradient. However, the problem is we can't easily backpropagate through the legacy solver because it is not automatic differentiable usually. To resolve this problem, we have developed a method that allows legacy solvers to be compatible with backpropagation using an unbiased and low variance estimator of gradient. There are three key components of this method. One is forward gradient, which is an unbiased estimator of the gradient. It is very easy to compute, but has very high variance. To reduce the variance, we train a surrogate model imitating the behavior of the legacy solver and construct a new low variance estimator based on control variate method. We applied this method to PET-C and accelerated different kinds of solvers for different problems. So far, these are all linear solvers, but the methodology is not limited to linear solvers, but applicable to a very wide range of solvers. Now we are applying this method to learn good turbulence models in OpenFOAM. If you are interested, please check our paper for more details and discuss later. Thank you.
Next speaker, Moritz Schwarzmeier, please.
So hello from my side and welcome to my talk about formatting of OpenFOAM code. I'm bringing greetings from the research software engineering SIG, where we have been dealing with this issue for the last few months. So we are working on automating code formatting because honestly, if I show you this slide, it's a waste of time to review this. Anyone can tell me within the next 3 seconds what the difference is between left and right? Exactly, there is none. It's only the formatting. There's a few spaces that have gone. There's someone who indented 2 levels instead of 4. There's in the last line, someone broke something because people were not sure if it's 80 characters. So one decided it's 80, one decided it's less than 80. And honestly, there are tools that can do that better than I, because I don't know. I don't like counting to 80. Don't know about you. So we've been working on automating this. This is an ongoing effort in our SIG. and we would be happy if you can contribute. You don't have to read the full style guide, which is 9 pages, by the way, if you would print it to PDF, which probably not everybody has in full length, especially students working on a thesis for 6 months. They just won't have the time to do so if they want to get anything done in open form. So then the supervisor, who's paid like, I don't know, $80,000, sits there and formats the code by himself. That seems not ideal. There are tools out there who do this. We're going for automatization with Clang format. So if you would like to contribute either to this or to other topics, we would be more than happy to welcome you on our next meeting, the 12th of July. There will also be a talk on build systems. Yes, so coming with this automation, might be a few slight changes to the code formatting, because OpenFOAM has a few styles that are very special to it, which we won't be able to reproduce, but we will try to stay as close to the original as possible. And since it's automated, I don't think you really have to care. Just be aware there's something coming, and maybe see you in the next meeting. Thank you.
Thank you very much. So, the next speaker, Martin Izud.
Okay, hello. Yesterday I met Miguel during coffee break, and he said there is still a possibility to apply for a splash talk, which from my point of view means I can do a promo of our work free of charge. And because of the format, I cannot be asked questions directly after, so win-win. And here's the promo. For the last 5 years, in our group, we've been developing a code. Well, these are not the correct slides. I'm sorry. Okie doke. Yep. We've been developing a code for direct numerical simulation of flows with arbitrarily shaped particles. If you are interested, this QR code will take you to the GitHub repository of ours. And now let's see a little bit more into the code. This is our digital viscosimeter here. So here we have no slip boundary velocity. Here we have some prescribed velocity, and we measure, in this case, apparent suspension viscosity in here. In the code, the solids are included through some version of immersed boundary. The solids themselves are treated through discrete element method, which is actually our own implementation. It can take into account basically any particle shape if you can define it through STL, so the same stuff as you used for Snappy Hex Mesh. And everything is directly in open form, with a little bit of cheating through standard library, but the final solver or the final library is actually purely open form. And now let's see how this viscosimeter works. To our surprise, actually quite good. In here we have 3 different types of particles. We have spheres, and everybody can do spheres like lights and stuff, but we have also rods and these glitters. And we have experimental data for this, so we can compare how these suspensions, how the apparent viscosity of these suspensions behaves in dependence on the volume fraction of solids in there. And you can see that for this case, so in green we have spheres, and there are simulations and experimental data. Then blue are the rods, up to the 42% of solid fraction, and red are the glitters. And the agreement is quite good for this. So this is a promo slide, but that's not the only stuff the code can do. So here we have, for example, some ugly particles. We can let them fall. This is just pure DEM falling, so no fluid. But we have open foam on the other side. So we can plug in flow, and we can do some nice fluidization animation, which, well, in this case wouldn't run. So this is just an image. So to conclude, the project is called OpenHFDEIB DM. If you are interested, scan this code. The development is a collaboration between our group at the Institute of Thermomechanics of the Czech Academy of Sciences and the group Monolith at the University of Chemistry and Technology in Prague. And that's all from my side. Check this out. Contact me if you are interested.
Thank you. Perfect. Next speaker, Jianhao Wang.
Hello everyone, good morning, and it's my first time to the Splash talk, and I'm very happy, and my talk is about the self-DFEM method for the predicting slamming loads and structural responses of a stiff wedge. And as we all know, a very brief background introduction, and we know the ship will experience slamming events, and mostly we are simplify this kind of study to a simplified wedge-shaped water entry problem, and which in this case, hydroelasticity must be considered. And to do this kind of simulations, we are using 3 different open source tools. First is the OpenFOAM. As we all know, it's used for the fluid dynamic simulation, and we can calculate the hydrodynamic forces and also the rigid body motion. And also we are using a open source tool calculix to do the structural side calculation and to compute the flexibility, and also we are using Precess to do the data exchange between them. And this is geometries and also the competition setup, and we have done some experiments in a towing tank, and also this is a model with flexible parts, and this also has some transfer response here to strengthen the structure, and also this is a computational grease. And this is okay, it cannot work, it's an animation, and just following down to the water, and we can find the duration of the pressure distribution, also some structural responses, and we can skip this, and we can find some results here. We have compared our results with the experimental data, and we can have a very overall good agreement with the experiment data, and in this case we can have an average error of below 10%, and also this is results for the structural side, and we can also have a good agreement with the structural stress. Yeah, and this is some simulation results of the flow field and also the structural response, and we can have very much details of this kind of problem, and we can have the distribution of this like the sprays and the jet height, and also the structural response, and we can find some 3D-dimensional effects due to this kind of structural response, since there is a transfer response here, and this can help us much better to understand the complex fluid structure interaction problems. And that's all for my presentation, and thanks.
Thank you very much. So, and the last splash talker is Wenmen Zhao, please.
Okay, thank you for your introduction. And I'm Wen Zhao from Shanghai Jiao Tong University, and today I'll talk about something about the wall model LES for turbulence boundary layers. So why we need a wall model LES? As you may know, if you want to resolve the smallest scale in the boundary layer, you must take most of the efforts to your computational mesh about over about 90% of the computational mesh will be used to resolve the inner boundary layer. So that's the motivation why we want to use the wall model LES. If we model the inner layer, it will be the computational grid will be reduced significantly. For the wall model LES, the required grid points is the order of the Reynolds number. So we have carried out the wall model LES on a turbulent channel flow on the Reynolds number 1000 based on the wall friction velocity. And we also did some comparison with the wall-resolved LES. This is the boundary. This is the computational domain we used for the turbulent channel flow. And this is the case. And also, this is the computational mesh. We can see for the wall-resolved LES, there's very dense mesh near the wall boundary. And however, for the wall-modeled LES, since we have modeled the inner boundary, the mesh in near wall is relatively coarse. And this is the preliminary results. This is the instant noise flow field extracted by the Q criterion. We can see for both wall model and wall resolved LES, there are some multi-scale vortex structures also captured. And we have also compared quantitatively flow quantities such as the mean flow profile, and we have compared with our GFM paper, and this is the DNS result. We can see the wall model, the LES result is somehow underpredicted the mean profile. This is because the friction velocity is underpredicted by wall model LES. But that's not too bad, as well as the Reynolds stress is also not very bad. And also we have compared the TKE budget term, such as the production term, the transportation term, and the dissipation term, etc. And we can see that in the log layer region, the result is not bad. And we also compare the fluctuation. This is very important. If we model the inner layer, we may miss in some small scales. We should maybe we should pay attention to the fluctuation. From the result, we can see that the wall model is slightly over predicted the fluctuations. And this is the two-dimensional spectra which present the space-time correlations. And for the velocity fluctuations, the wall model LCS is not very bad. But for the wall pressure fluctuation, wall model LS has some deviations compared with the DNS result. So in summary, we have conducted wall model LES for turbulent boundary layers, then mean velocity and Reynolds stress, as well as the TKE budget is very good in comparison with DNS result. However, wall model LES overpredicted the wall pressure fluctuation spectra, and one of the most important is the wall model LES will save the computational cost up to about 20% CPU hours compared to that of resolved LES. That's my talk. Thank you.
Thank you. So let's thank again the Splash Talkers. Thank you very much for your cooperation.